Hello, my name is Frank McKenna. I'm still here at UC Berkeley working for the Neary Sim Center, a National Science Foundation funded project. This is a video demonstration of how to use OpenMP to write parallel programs. In a process, we have our stack. This is program memory. We've all seen program memory. We have the stack, we have the text data, that's where the instructions are about the program. We have data, initialized and uninitialized data section, and we also have the heap. With threads, we have these lightweight processes. Each of these lightweight processes, they share the heap, they share data, they share text, and they each have their own stack. When they start off, they're given, it's like creating a procedure, but each thread has its own stack, and therefore the variables they have in the stack are unique to that thread. So if we spawn two threads and we spawn them actually with both running function A, they both would have var1 and var2, but to each of them var1 and var2 could be different. That's the idea of threads. Threads are created dynamically, sort of mid-execution. Each thread has these private variables that are in the stack, and they share the other variables that are in the heap and the data. Now the threads communicate via changing by that shared data. They're reading and writing to the shared data, and that's how the communication is done. There's no send and receive selves. The communication is via that shared data. And they have to communicate when they're accessing the shared data through synchronization so that they don't overwrite or change things they don't mean to do, as it will lead to something called race conditions. So the model for thread is we have a master process that starts at some point. The master process decides it's programmed that will start some threads. So we have all these threads are created. So this is a parallel area of execution. When that work is done, it comes back to the master, who works alone and sequentially again. At some point, they'll spawn the threads again. We come back to master, spawn some threads again. So we have some parallel regions, sequential regions. And when we're looking for performance, we want to minimize the duration of these sequential regions so we can get to our perfect speedup. So just like message passing, there are a number of options. The two most popular are POSIX threads and OpenMP. Today we're just going to be looking at OpenMP as it makes threaded programming very easy. So OpenMP is actually built into many C, C++, and Fortran compilers. As I mentioned, in the threaded environment, the threads communicate by sharing data. We can lead to race conditions. Race condition is when a program, you run it multiple times. Each time you run it, you get a different answer. OpenMP provides constructs, as we'll see, that make it really easy to define where the threads were spawned. And it also allows us to control how the data is accessed. We can synchronize very easily in OpenMP the access to the shared data, which will minimize or reduce reduce altogether the race conditions. We do not want race conditions. So OpenMP, there's basically two things we have to know about. One is what are called compiler directives, the pragma. So there's pragma OMP parallel is a directive to the compiler that this is a place to spawn some threads. We'll see it in an example in a moment. In addition to these pragmas, we also have runtime library calls, where we're basically calling libraries from the OMP. We're basically calling functions from the OMP library. Again, we'll see this in a minute. And being compiler directives, they're actually built into the compiler directly. You just have to tell the compiler when you run the compiler that, hey, you want to activate the OpenMP. In GCC, it's a -f OpenMP when you compile a file. When you're using the Intel compiler, it's a \q OpenMP. And I'll show these when I demonstrate the running of an OpenMP. So, like I did for Introduction to C, C++, MPI, here is Hello World for an OpenMP program. So you see I have this include OMP.h. This is where I'm pulling in the OpenMP library functions. I include my standard io.h as usual, int main, and here I have this pragma OMP parallel. What this tells the compiler is upcoming there's going to be a block of code, and for that block of code I want you to spawn processes, or I want you to spawn threads, and I want each thread to run in parallel inside this block of code. Now internally what this done is, remember, it's creating a stack for each thread on the in memory, and any variable that appears in here will be unique to that thread. So here's the block of code. So let's get over this. I'm creating an integer ID. So each thread again has its own unique stack. All the variables in here will be unique to that thread. So ID is going to be an integer. They'll all have an integer. It's set equals to what the result of OM3P get thread num. So this is this unique ID for each thread like we had in the MPI. NumP again, this number will tell you them how many threads are actually running in the computation. And then print hello world, I am, ID of the number of threads that are in the computation. Return 0 when we're done, close curling braces. So that's a parallel threaded program that will run on your computer. It'll use the cores on your computer. There's nothing in here indicating how many cores we're starting. When we run it like this, we're just relying on how many the operating system is going to give us. We'll see later we can set the number of threads that actually run. So let me now go over to the terminal and demonstrate this on Stampede 2. So here I am, design safe, SimCenter Bootcamp. Let me cd to the code, parallel, OpenMP. So I have a whole bunch of files in here. Hello 1.c, there she is. So the first thing I want to do is I want to change the module to module load GCC. I'm going to use GCC. So let's compile hello world. So remember the compiler, to get the OpenMP, we need the -f OpenMP with the compiler. Hello 1.c. Now we need to go to IDEV. So you see I started IDEV with N1, N16. So .a.out, let's see what happens. So we only got one export, OMP num threads equals 4, say, and we'll run that again. And we get 4. And there's another way to do this. Hello 1.c. I could have actually done 2 ways. I could go invoke a function OMP set threads. Let's do this too, something different. So invoking the function OMP set threads. Let me compile that. GCC -f OpenMP hello 1.c. Let's run that. There I got 2. I could do this one other way too, just to confuse you. Not intended, but this also has a purpose. We could put it with the pragma directive. It's a little bit cleaner. Okay, so that's the thing, what it looks like now. Basically, I'm doing this pragma OMP parallel, and then I just specify num threads as 2. Actually, let's just, so we change it again. We'll go back to, let's do 8 this time. Compile again. And run it again. There we go, I got my 8. Okay. That's something I'm going to present in the slide. Let's see if it happens. Basically, I'll get a different output. Yeah. Well, did I? Yes, I got a couple of. The order these things are produced is slightly different. It's a. It's just an example of how race conditions can happen. So let me exit and back to the presentation. So we are back in the presentation. Changing the number of threads. Actually, I already showed you this. There's that command where we can set it above the pragma. I guess the thing to point out that I didn't mention that this is a request. You're not actually guaranteed that. You always, inside the pragma, need to get the number of threads that were actually provided. Done it again. So again, that's what I showed you this. We can actually put the number of threads in on the pragma line. And then here's one where we could actually do, 2 blocks of threads. Here we go. The master spawns 2 threads, comes back, spawns 4 threads. The notion of race conditions where you can get different answers every time you run the program. Here I don't really care that I'm getting different output. But if I'd been in here and playing with variables and I'd somehow overwrote one variable with another, and when then I go to print it out, I'm getting a different output depending on which one gets there first. That's sort of a race condition. So you just have to watch out for it. So threads, typically, what do we want them to do? We want to do the parallel stuff, the pragma OMP parallel, and then there's also pragma OMP parallel 4. And then we also have to worry about the shared data, and that's what we're going to do in these next few slides. So this first slide, we're doing sum. So we want to do a parallel loop. So we want to share some data, do some work, do some actual work other than hello world. So here's my pragma OMP parallel. I get my process ID, or the thread ID, the number of threads, and then I'm going to do something based on the thread ID and the number of threads. I'm going to invoke this function SumVectors. What does SumVectors do? It takes in n, the 3 arrays A, B, C, and then the thread ID and the number of threads. It figures out where it's going to start and end its loop. We're going to run through the thing in a for loop. This is how we do it. So once I figured out the starting and ending point, then I just blast through my normal loop. So what this is doing, here we come, we're coming in the master, then we branch out, we create a number of threads. We start one with 0, 4, the next one with 1, 4, 2, 4, and 3, 4. And then all the threads come together again, and then we march on. So these were the results I was getting on my Mac. As you see, I'm getting improvement in the performance a little bit, not too good. Because the for loop is such a widely used thing within threads, they've got a special thing in the pragma for it. So we can have this pragma OMP parallel this pragma OMP parallel, and then inside the pragma, just before we have the for loop, we do tell the compiler that here we're going to have a for loop, and we want it parallelized among all the threads. So we don't have to change our code, but the compiler will automatically parallelize that among the threads in a similar fashion to what was done inside this code here. The nice thing is the compiler is doing it for us. And if the whole pragma is just going to be doing one big for loop, then you can do that pragma OMP parallel 4, that whole loop would then be parallelized. So now what about the dot product? Can we do the dot product in a similar way? So here I'm doing the dot product. So what am I doing? I'm the thread ID and then I'm threads as always. I'm also on process 0. I put in the sort of the global data space num threads. I tell num, I come back with num threads. I fill it in on numt. Remember, these variables go away when this thread stops. When this stack goes away, these variables will go away. So I just want to hang on to that numt. And then I loop over the thing. I start at the thread ID, data size, and then I increment by the number of threads. And that will do that. That'll go through that. That'll go through the array. And this sum, the result for each thread, I put into an array. So I'm creating an array, and the result for each thread, I'm going to go 0, 1. Each thread, like thread 0, we'll put in sum 0. Thread 1, we'll put in sum 1. So in the end, when I'm done, I'll have all the sums from each thread inside an array, and then I just sum them all up to get the total. You think of doing this when we do pi, but this one is not great performance. The reason is this cache, and the reason is sum. The problem is all the cores, they've got sum in there. When they're writing to sum, they're bringing it into the cache, and then when they're all writing to one variable beside another, they keep causing the thrash to thread. It's termed what's called false sharing. As you see here, I've got the thread 0 and thread 1, or thread 2 are trying to write to their variables. If their variables just happen to be on the same cache line, they're both in the level 1 or level 2 cache. So what the hardware is going to do automatically is dump the cache out, tell everybody else they're going to write to it, which stops everybody else writing to it. And then when they write to it, the others have to bring it back into their cache. So this takes forever. There's a lot of thrashing going on. So the solution, basically, we want to pad this thing so these things are not side by side. We do that just by saying it's a 2D array. So we pad the array. If you remember from the first day what that does to the memory layout, we've got big differences between the values in the same column. So now when I do it, I just do the same thing, same code. The only thing I've done is I've always put in the results in TID 0. When I'm done again, I sum it up and I get the result. So a way to avoid that altogether, having to put it away squirrel it away in a place like sum, is to use this thing OMP critical. What OMP critical, it synchronizes the access to a variable that exists outside in the global space. So this is our data space, this is our initialized data space in the program memory. And what we're doing is we're controlling access to it, so only one thread gets in here at one time. Therefore, we can't have two threads writing this at the same time. Notice we don't want to put the critical section around the for loop because we want things to be running in parallel. And then the final thing, the way that we could implement this is using what's called a reduction. And here you just say that I'm going to be doing a reduction on the dot. The dot being this variable here, and it's going to be an addition. And then you don't have to put any OMP critical, it just does the same thing. The critical, you could put a little code block around here, so this could be a bunch of lines that we're working on. If we're just doing the dot, it's just like one variable you get to play with, one line. And the additional reduction operators, as they're called, is, what's the initial value on the dot? When we're doing a plus and a minus, it starts at 0, and when we do times, it starts at 1. Pitfalls for parallel loops. So it looks real easy to parallelize a loop. You just go in there, throw a pragma around it, and off you go. The problem is these loop diff carry dependencies. This is the code I write. I like it to be x plus equals delta x. The problem is if I'm doing this in one of these my parallel loops, the resulting x is not right. Basically I'll be just getting the wrong x all the time when I go into my pi routine. So what I explicitly have to do is I have to take this dependency out. So I have to explicitly say that x is equals to. I have to explicitly calculate x inside every loop, just so that I don't get the wrong answer. And this is the example we're going to do. Again, it's the pi. We did it sequentially. We did it for MPI, and now we get to do it for OpenMP. And it's similar to the dot calculation. So there's multiple ways to do it. So if you finish this early, In the exercise, try another way, see which way works best.